So I just want to get some more practice with doing this translation theorem. So let's look at example 8. We want to take the Laplace of cosine of t times the unit step of t minus pi. So if we were to apply this theorem, which is number 53 on our table, then we would have e to the negative as, our a is pi, times the Laplace of our g of t plus a. So our function is cosine of t, but we're going to replace that t with t plus pi. Now we're going to have to simplify that. So that's going to go back to your sum and difference formulas from 172. So going back to that calc cheat sheet, we know cosine of alpha plus beta is equal to cosine of alpha cosine of beta minus sine of alpha sine of beta. So let's plug in what we know. We want to simplify cosine of t plus pi. So that's going to be equal to cosine of t, cosine of pi, minus sine of t, sine of pi. Now sine of pi is 0, so that piece is gone. Cosine of pi is negative 1, so we're going to get negative cosine of t there. So this guy's going to simplify nicely. You always want to simplify before you try to find the Laplace. If you can, it's just going to make life easier. And then we could pull that negative out. And then now we want to find the cosine of t, the Laplace of the cosine of t. And if we go back to our formula sheet, cosine of t was number 8. And it says it's s over s squared plus k squared, and our k is 1. So there's our Laplace. So I want to do just a few more of these to kind of get really familiar with these formulas. So let's do another example. Let's say we want to find the Laplace of t minus 1 unit step t minus 1. Well, if we go back to our cheat sheet, we've got t minus 1, u of t minus 1. That ends up being number 52. So then it's going to be e to the negative as times our capital F of s. So in this case, our as, a is 1. But we need to find the Laplace here and here. Notice they're the same, so we're treating that kind of like a t instead of a t minus 1 there. So then when we find that Laplace, it's going to be 1 over s squared. So there's our final answer for that. You really have to pay attention to how these are set up. It's a little tricky. Let's do another one. So notice that exponent is really similar to what we have here. If we were to factor a negative out, it would be identical. So using number 52, we have t minus a in both places. So then we can use this. So it's going to be e to the negative as times f of s. But remember that f of s is the Laplace of our t. So it's e to the negative as. Our a is 2. And we're treating this, let me write it in a different color. We're treating this guy like a t. even though it shifted to the right 2 units. So we're finding the Laplace of e to the negative t there. So we have e to the negative 2s, and the Laplace of e to the negative t, going back to our sheet, would be 1 over s minus negative 1. So final answer would be that. And let's do another one. Let's say we want to find the Laplace of 3t plus 1 times the unit step of t minus 1. So it would take a lot of work to try to rewrite this in terms of t minus 1. That's where that alternative form of the second translation theorem is going to come in handy. So what if we were to view this as our g of t times the unit step of t minus 1. So then it's going to be e to the negative as times the Laplace of g of t plus a. So we're viewing that g of t in this case as our 3t plus 1. That's our g of t. So using that translation theorem, I'm going to scroll down because I want to point. We're using that guy, right? So we've got g of t, we've identified it. So it's going to be e to the negative as. Our a is a negative 1. Sorry, our a is positive 1 because of this guy. And then it's going to be the Laplace of g of t plus a, and our a is 1 again. So here's our g function. So now we have e to the negative s times the Laplace of 3 times t plus 1, and then plus 1. So we replace this t with t plus 1, since that's what our theorem tells us to do. And remember, we did derive that, so we can use it. So we have 3t plus 3 plus 1 as a plus 4 there. So if we take the Laplace, this is going to be 3 times the Laplace of t, and the Laplace of t is 1 over s squared. And then this is 4 times the Laplace of 1, which is 1 over s. So our final answer will be this. So you can see how we have to identify what our g of t is, identify a, substitute everything in, and then we have to rewrite that function, substituting t plus a in for that t, to use that second translation theorem. I want to do one more. Let's do another trig one for fun. Laplace of sine of t unit step t minus pi over 2. So applying that translation theorem, the alternative form, is what we're going to use here. So notice our a is pi over 2, so I'm going to write that over here. The last one, a was 1. So it's e to the negative as times the Laplace of g of t plus a. So our g function is sine of t. So we want to replace that t with t plus pi over 2. We're replacing it with a new improved version. So now we really need to simplify this guy. So I'm going to do this down below. So that's one of your sum and difference formulas back from 172. So we have the sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine of beta. So sine of t plus pi over 2 is equal to sine of t cosine of pi over 2 plus cosine of t sine of pi over 2. So we know cosine of pi over 2 is 0, sine of pi over 2 is 1, so this guy just reduces to cosine of t. So that's some side work. So rewriting, that's really the Laplace of cosine of t. And we know the Laplace of cosine of t is s over s squared plus 1. So there's our final answer. So we can take the Laplace of something that's in terms of unit step, but now we need to be able to go backwards. So let's talk about the inverse Laplace. Let's say we have this guy. We have 1 over s minus 4 e to the negative 2s. And we want to take the inverse Laplace of that. And we're going to end up getting something that's in terms of that unit step function. Now notice when we do that, this is really what we're looking for here. What is that inverse Laplace for that? And then when we figure that out, we're going to replace that t with a t minus a here. We know this is going to be a unit step because we have that e to the negative as. So let's look at a. We want to take the inverse Laplace of 1 over s minus 4 e to the negative 2s. So we're really just going to focus initially on this guy. If we were to take the inverse Laplace of that, then that would be e to the 4t. But because it's multiplied by this guy, that indicates that we need a unit step function here. And it's going to be a t minus a. Now our a ends up being 2 here. It's the number after the minus. So we're going to replace what would be a t here with a t minus 2. So there's our inverse Laplace. There's not a lot we could do to simplify that one unless we wanted to distribute that forward. I'm going to leave it like that. Let's look at b. We want to take the inverse Laplace of s over s squared plus 9 e to the negative pi over 2s. So we're going to really focus initially on this. This just means we're going to have an inverse, a unit step function. So that 9 could be rewritten as 3 squared. And this ends up being the cosine function. So it would be the cosine of 3t. We're just going to plug in something different for t. That unit step piece is going to be t minus a. In this case, our a is pi over 2. So we have a t minus pi over 2 here. We have to have the same thing here. Now, this guy is going to simplify, so I'm going to simplify that down here. So this is really cosine of 3t minus 3 pi over 2. We're using those sum and difference formulas. So this is cosine of 3t, cosine of 3 pi over 2, plus sine of 3t, sine of 3 pi over 2. So we know cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is a negative 1. So all this reduces to negative sine of 3t. So this guy's going to become negative sine of 3t times that unit step t minus pi over 2. So there's our final answer. So I want to do just a couple more of those to make sure we've got that concept. So let's do another example. Suppose we want to take the inverse Laplace of e to the negative 2s over s cubed. So we can rewrite this. We have 1 over s cubed, e to the negative 2s. So remember that e to the negative 2s, that's e to the negative as. That just means that we're going to have a unit step function involved. This, guy, is what we really need to focus on initially. So that almost looks like our t squared. Going back to our table here. If we had a 2 for that exponent, we would have 2 factorial over s cubed. But we're missing that 2 factorial. So we can multiply it in as long as we compensate outside the problem. Now, 2 factorial is just a 2, so this is really just a 1 over 2 there. And then when we take the inverse Laplace of this, we're going to get t squared. And then remember, this is all multiplied by that unit step. We know that because of this piece of t minus a. Our a is 2. So then instead of putting t squared here, we have to replace that with a t minus 2 instead of just a t. Remember, these guys have to match to use that formula up here. They have to match here and here. Let's do one more, just to kind of make sure we get our feet wet here. So inverse Laplace, 1 plus e to the negative 2s squared, quantity squared, over s plus 2. So let's square that numerator. That's our first step. So if we were to square that, we're going to have a 1 plus 2e to the negative 2s plus e to the negative 4s. And all that's going to be over s plus 1. Now, we're going to split that numerator. And I'm going to do 2 steps in one here. I'm going to split the numerator and separate the pieces. So there's our first piece if I put 1 over that denominator. Here's our second piece. If I put 1 over the denominator multiplied by e to the negative 2s. And then that last piece would be 1 over s plus 1 multiplied by e to the negative 4s. So, first piece is easy. This is in the form of s minus a. Our a is a negative 1. Hold on a minute. My 2 became a 1. Let's change this guy back to a 2. Sorry about that. Should not be doing this late at night. But it's more fun late at night. There we go. So I'm just keeping the same problem. S plus 2 there, and so on. So this guy. This is in the form of s minus a. Our a is a negative 2. So that's just straight off the chart. That's the exponential one, which is number 11. So it's going to be e to the negative 2t. This guy, we really have to focus on this piece first. This just means it's going to be multiplied by the unit step function. So that piece is also going to be e to the negative 2t. But we can't just put t in. We have to put t minus a in. And in this case, our a is a negative 2. So remember, our a is coming from the exponent on the exponential when we plug in here. Remember t minus a. So we've got two a's here. We have to be careful. There's a piece for the exponential, and then there's this guy up here in that exponent. In this case, our a is 2. That's the a we're referring to here. So we're going to have a t minus 2 there. What we put here, we have to put inside here. Just replacing that regular t with a t minus 2. And then same kind of thing for that last one here. So we're going to really focus on this guy. Our a here is going to be a 4 based on this exponent. That also tells us it's multiplied by the unit step. So we have e to the negative 2t again, times the unit step. In this case, it's t minus 4. So we have to replace with a t minus 4 here. These guys have to match. These two have to match. So there's our final answer for that one.